I tried to move it 8 minutes over my hot.
Okay, let's get started. I'm not sure why this is highlighted yellow. That's new, but yeah, it's an updated enhancement, I guess. I don't know. It's very weird that it's doing that, but oh, it's paused. Oh, maybe that's why. With that, thank you. You would think it'd be under the share, but you guys know the technology better than I do. Okay, last thing we did, shrink this down, is root locus rule number 5, right? Which, if we have to leave the real axis, we have to find the breakaway or break-in points. And so what we saw was we were taking the partial derivative of our k function, right? Because we're solving the function for k. And it's a partial because we're taking it with respect to s. We set that equal to 0. And then we're allowing ourselves to actually be able to find those breakaway points. What's also really good is this right here, that k term actually gives, or this equation, I should say, gives us an equation to solve for any value of k if we have a valid root. So if you have a valid point, like say you're looking for a performance characteristic, and you say this point looks like the performance I want, you actually can just calculate k from the root. So you don't have to guess and check. You can actually solve for that. So this is really going to be a magnitude only. Anybody want to guess as to why it's magnitude only? Because k is a real coefficient, right? It doesn't have a magnitude and an angle. It has to be a real coefficient. So don't forget, there's a magnitude and an angle associated with the root locus, but k in and of itself is a magnitude only term. So we don't have to worry about the angle part. So we've done a lot of work to get everything on the real axis and figuring out where we leave the real axis and doing all those things. What we haven't really done to this point is if we're not on the real axis, so if we have poles or zeros that are not on the real axis, they're out someplace in the right-hand or left-hand half plane, how do we actually solve for the root locus or actually start to be able to draw it? So one thing we're going to do is either exiting or departing from, is it a pole or a zero? If we're not on the j omega axis and we want to depart, would we be departing a pole or do we depart a zero? What's our mantra? You start at a, guess the mantra didn't work, right? Start at a pole and end at a zero, right? So you're departing a pole because you start at a pole and then you depart from there and then you end or arrive at a zero. So you're calculating departure angles if you have complex poles, and you calculate arrival angles for complex zeros. Okay, so there is a difference between the two. All right, so let's take a look at, whoops, sorry about that. Let's take a look at this one. And we have a transfer function, right? We have the open loop transfer function. So we know that we have a 0 at -2, and we have a pole at -3. And if we did the quadratic equation, we have two complex poles at -1 plus or minus j. So the first rule of thumb is where does the root locus live on the real axis? Remember what we did last class where we calculated all those angles? We ordered the poles or zeros, right? Between there. And then we said that on the j omega axis, it lives to the left of an odd pole or zero on the j omega axis. So it only lives between -2 and -3. And it starts at a pole, ends at a 0. I guess I have to say that a lot more because that helps us with our direction of our arrow, right? Now, that branch is done. we have two more branches, right? Because these are starting at some x that's complex and ending at zeros. And those zeros are going to be infinites because m is equal to 1 and n is equal to 3. And remember, the number of poles or zeros at s equals infinity, in this case it's zeros, number of zeros is equal to n minus m, 3 minus 1. So we get two poles or two zeros at s equals infinity. And so those are someplace out, we don't know what those are yet. We would have to do the asymptotes and all that stuff. All we want to do at this point, because we know we've already figured out how to calculate asymptotes, we want to figure out what angle are we departing from, because again, these are poles, right? Those are two poles. So what angle do we depart from those two poles? So our mantra again starts at poles, ends at zeros. We already have the one segment on the real axis. The departure, okay, it's going to be determined by, you have to pick a point that is near one of the complex poles. How about basically right at the pole? And we know for it to be a valid root locus plot, we know that our 1 plus kgh has to equal 0. So kgh has to equal -1, which means the angle of kgh has to equal plus or minus 180 degrees. And then r times plus or minus 180 degrees, right? Because we just keep going from there. So we know we're going to have to be equal to 180 degrees or some multiple there. All right, so here is our angle calculation. And sorry that it's hard to see. I guess I'll move that up over here. Keep moving it around. So we've got to calculate this departure angle here. So the first thing we're going to do is we have a theta sub P1, which is what is the angle that goes from that one complex pole to the other pole. Then we have an angle for our zero, again, leaving that zero and going over there. And then finally, our last pole, calculating an angle from there. The P2 is an unknown, right? That's what we're trying to get to. So we know that that has to equal, sorry, I keep moving this around. That's going to have to equal those multiples of 180 degrees. And since it's a pole, it's a departure angle. So our angles are theta Z1, theta P1. We'll throw in our departure angle here. And lastly, that's our point there, right? So this point is really, really close to that final pole. So now we have to start calculating angles. So how do you calculate this angle for theta Z1? Let's see if we get our thinking caps on. How do we calculate theta Z1? You don't know how to calculate theta Z1? Should be pretty easy, right? Isn't it a right triangle? You can't calculate this angle? Anybody? Close. Sakatoa says what? The tangent of theta Z1 is equal to the opposite, which is 1 over the adjacent, which is 1, isn't it? So theta Z1 is equal to the inverse tan of 1, which, ain't that 45 degrees? 45 degrees. Why did we put the minus over here? We did this 2 classes ago. Do you remember the math where we had multiplying or dividing complex numbers? We either added angles or subtracted angles. And since all the zeros are in the denominator, those are all going to be subtracted. Okay. All right, so let's do theta P1. Now you're all pros at it. How do I get theta P1? Anybody? Inverse tan of what? Of 1/2? Is that what you said? Yeah. Well, I do the opposite, right? What's the opposite over here? The opposite is -1 to 1, so that's 2. What is the adjacent? 1? Theta P1. Okay. It's 0, isn't it? You're going nothing whatsoever in the x direction. So it's, you rise 2, and then you run 0, right? Which is a good thing. Because what's the inverse tangent of infinity? 90 degrees? It is? You don't remember? Put in your calculator, put the inverse tangent of, well, put it in the inverse tangent of 10. We can do it in MATLAB too, right? So I'll do a tan of 10 times 180 over pi. So we get 84. Now I'm going to go 1,000. 89. Now I'm going to go 1,000,000. 89.999999, but it's not 90, right? You get 90 degrees, yeah. Do you all not, you were not taught how to get 90 degrees? What's that? But that's a question though, seriously. In your pre-calc or 122 class, did they not explain that the inverse tangent of 90 degrees is inverse tangent of infinity is 90 degrees? Yeah. I was gonna say, if you can't see it, I mean, if you do the math, it proves it out. But over here, what do I need to rotate to get straight up from where I am? From the 0 axis, I have to go up 90 degrees. Okay. Since we're struggling with this, let's do theta P3. This is the inverse tangent. Well, let's do the first one. It is opposite, which is 1, over the adjacent, which is 2. So the inverse tangent of 0.5, which if you plug that into your calculators, should be, what was that, 28.5 degrees or so? Sort of. We can do that here. So instead of 1,000,000, let's do 0.5. So 26.6 degrees. All right, so we have 45, and this angle over here is 26.6, and that has to equal plus or minus 180 degrees. When I do all my math, what I end up with is theta D, my departure angle, is 108 degrees or minus 252. So I have to rotate all the way over here, right? 108 degrees, and that's where it departs. And I don't need to calculate this one. Why? Because you have to have complex conjugate pairs, right? So you know if it goes up in that direction, it has to go down in that direction as well. But if you also did the calculation, you would end up with minus 252 for that complex pole. So here is our rule number 6, which is, I don't know if you want to call us our last rule, but it gives us our sort of our final rule to be able to draw these. We do have one sort of additional rule we'll get to in a minute, but our angle of departures, theta z minus theta p plus r times 180. My arrival angles, theta p1 minus theta z1 plus r times 180 degrees. And you'll notice over here, the reason why that is shown as that way is because when you do the math, remember our arrival angles are arriving to a 0. So all these terms get swapped around. So it becomes theta p minus theta I. All right. If you don't necessarily see that, we have that. Well, we can do that over here, right? We can say that if this is a departure angle, if we're trying to calculate an arrival angle, we have theta A minus our theta P's equals R times 180. And we might have 5 of these. So let's say we have theta, let's just put theta Z1. When we bring these to the other side of the equation, that's where you can see the negative becomes positive and the positive becomes negative. So that's how we end up with a positive number here and a negative number here. All right. So in summary, we'll do the last one here. So how, if these cross the j omega axis, if they somehow cross back over here, how do you determine that? So first off, we have to check the angles of the asymptotes, right? If the angles of the asymptotes are plus or minus 60 degrees, you know that this is going to go back and cross the j omega axis. So how do you know when it crosses the j omega axis? Is there a way that you've seen thus far in this class already that might help you find those points? Again, this is just a refinement thing. Is there anything that you've done thus far? Because remember, K is changing. Anything that you've done thus far that will help you find where it crosses the j omega axis? Might have been on our last test. Problem number 1. When you end up with a row of zeros, what did you end up with? You had purely complex roots, right? Remember when we did Routh-Hurwitz? If you had a row of zeros, you ended up with purely complex roots. And how did you solve for, or how did you continue with your Routh-Hurwitz? You found the auxiliary equation, right? And the roots of the auxiliary equation are the complex roots. So that's what we do. We use the auxiliary equation to solve for that. So this is our summing. And again, we'll hold it down here, I guess, for a minute, because, well, maybe we'll put it way up over here. Here are the 6 sort of rules for building a root locus. Number 1, right? We know about symmetry about the real axis because of the complex conjugate. Number 2 is our mantra. Number 3 is the angle of the asymptotes is going to be R times 180. And remember, R is n minus m minus 1. So it's number of finite poles minus the number of finite zeros. That's the angles. And then where those asymptotes take off from, you find that as sigma sub A. The next one, which is the one we did a couple classes ago. So the root locus only lives to the left of an odd pole or 0 on the real axis. If we have to leave the real axis, we solve dk ds, set it equal to 0, solve for the roots. And now, our departure and our arrival angles, we just did. And if we do cross the j omega axis, we would find A of S only if crossing j omega axis, right? That's that little added sort of feature that we have to add in. All right, let's build a root locus for a system that has a basic, system. So we've got a controller gain, it's variable. We have to be given what the open loop transfer function is. We'll give you in a second. But then the next thing is, we want to determine a range of K that realizes our percent overshoot is less than 20%. Okay. So here's our transfer function. S minus 2 squared plus 4 squared. But those are zeros, not poles, right? So it's not necessarily an unstable system, at least yet. Then we have S plus 2 and S plus 4. So the very first thing that you should be asking yourself is, do I have to worry about asymptotes at all? Are asymptotes important to me? No. Why not? Because they're the same, right? The number of poles equals the number of zeros. Finite. So you have no infinite poles, do you? Or infinite zeros. So remember how over here, those, in this problem, you don't need to do number 3. Number 3 is gone. No work needs to be done. Okay? All right, so now we're going to go ahead and use number 4 and number 2 at the same time. Start at a pole, end at a 0, which is our second rule. And also where it lives on the real axis is to the left of an odd pole or 0. So we know our J, on our real axis, it lives here between the odd and the even. The problem is, and this is rule 2, we start at a pole and end at a 0. Somehow we have to get to those two fellas, which means we have to break away from the real axis. So we have to calculate step number 5, right? So we're going to do step number 5 and step number 6, including refining it to figure out where it crosses the j omega axis, because we know, whoops, what happened to mine? We know it's going to get all the way out over here, right? So we start in the left-hand half plane and eventually get to the right-hand half plane, which means we have to cross the j omega axis. So we have our points. Now we're going to calculate our breakaway points. Move this over here. So I'm going to solve this equation right here, the derivative of -1 over GH, and set that equal to 0. Does anybody not see how to get the derivative of that with respect to S? Do you need me to work it out, or do you feel like you can do it? Pardon? Okay. Let's copy this over. And bring up the whiteboard. Okay. Well, first off, does everybody know how I got -s squared, whatever? All I did was, you take -1 over GH, right? Which is -1 over s minus 2 squared plus 4 squared all over s plus 2 times s plus 4. You invert and multiply, and that's how you end up with this expression here. Okay, anybody need me to see me need to do that? Does anybody need to see me do that out? All right, so now we have to apply a rule. And that rule is the quotient rule, right? So we're going to take the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the numerator squared. Okay? So the derivative of the numerator, I'll leave the negative up front. Negative 2s plus 6. That multiplies the denominator, s squared minus 4s plus 20. Subtract from that the derivative of the denominator, 2s minus 4, times the numerator, and I'm going to move the negative out front over here, negative s squared plus 6s plus 8, all over s squared minus 4s plus 20, and that whole thing is squared. This gets set equal to 0, so when I multiply both sides, right, by the denominator, that term goes away. And at this point, it's just doing FOIL and all that stuff, and if you need me to do that, I can, to end up with that numerator. You can see I kept it over here, but I really only need it for this part here. Okay? Now, in MATLAB or Roots, I've got to go ahead and solve for the roots of this equation. I have negative 2.88 and 5.28. Are either of those valid, or are they, is one valid, or are they both invalid? Should be able to tell. Anybody? One's invalid. Which one's invalid? The 5? Why is the 5.28 invalid? Keep talking. It's not that it's unstable. It's, does a root locus live on the real axis over here? No, it only lives here. So how can you break away from the real axis if you're not there in the first place? So we know that this has to be a valid point because it's minus 2.88. That's the only place that it can realistically break away. So our breakaway point is minus 2.88. By the way, how would you solve for K? Right? Evaluate it at S equals minus 2.88. You just plug that in and you solve for the magnitude of that, and that's how you get K. The problem with that, though, is, well, that's not a problem. The K would equal negative 2.5. It doesn't exist, right? So we're not going to worry about that. So you can solve for K if you want to. I encourage you to do so because that's a pretty good idea. So now the next thing we need to do is solve for the arrival angles, not the departure angles, the arrival angles, because I'm arriving at 2 poles. So my arrival angle for one of the poles, so this angle, we have this angle here, right, which we already said is 90 degrees. We don't have to calculate that one. This angle over here is the inverse tangent of, let's see, we have to rise 4, and then we run 4, so that's equal to 45 degrees. This is 90. And then my last one is here. That's equal to the inverse tangent. We still rise up 4, but instead of going 4, we have to go over 6, right? So the inverse tangent of 4/6 or 2/3. So a tan of 2/3 times 180/pi is equal to 33.7, which we have here. So our arrival angle is the sum of the poles, right? Minus the sum of the zero angles plus 180 degrees. So this is a pole. This is a pole, so that's a plus. This is a 0, so that's a minus, plus 180. And we have approximately 168.7. So how does that arrive? You have to rotate almost that much to get to that angle. So it's going to be approaching something like that, which means you approach at that angle as well. All right, the last thing we need to do to get any refinement is where does that cross? So now we have to do our Ruth Hurwitz. Oh, I get the angles here. You can check those. So now we're going to go ahead and do our Ruth Hurwitz. So here's our closed loop transfer function. So we need our characteristic equation. Oops. Because we're doing Ruth Hurwitz, so we need our characteristic equation, which is 1 plus GH. So 1 plus GH equals that, right? It's 1 plus GH, and we have times K. So when we put that in there, we have S squared minus 4S over 20. That's the numerator. We don't care about this. We only care about this. So now we have to do Ruth Hurwitz. So here's our Ruth Hurwitz table. We have an S squared term. That's our highest order row. That becomes K plus 1. Then we skip and we go 20K plus 8. Then the nice thing is, because it's only S squared, we don't actually have to calculate 6 minus 4K, right? That just is the term that we put in there. All right, so now how do we solve for the value of K? Well, this has to be a row of zeros. So 6 minus 4K has to be equal to 0. So what does K equal? Six over 4 or 1.5, right? That's how we calculated our value of K. Once we have that value of K, now what do? We go back to this row, and my auxiliary equation, A of S, is equal to K plus 1, 1.5 plus 1, times S squared, plus 20 times 1.5, plus S. We set that equal to 0, and then we solve for the roots. And that's what we have right here. So we're crossing right here and right here. So here's our points, and that is our sketch for our value. Okay, this is hard because you've got this here and this here, you know this point and this point, and you know everything over here. This part right here just takes practice of how to draw. And so what you might need to do is you might need to try a couple points, right? Because once you know those, you know those. So you can get, you know, if you're struggling with how does it look, you can add a few points in there to go ahead and do your calculations. And that's our root locus. But it still doesn't answer the question, because the problem was we want a value of K that has a undershoot of, a percent overshoot, I should say, of less than 20%. So now that we have this, what are we going to do? How do we get a percent overshoot less than 20%? Will we get an overshoot? If we're over here on the real axis, there's no overshoot, right? It's an overdamped system. or it's potentially a critically damped system, but we know we have no overshoot. It's only once we leave the real access that we have overshoot. So how do we limit it to less than 20%? Remember this from second order systems? Theta over here is equal to the inverse cosine of zeta, right? So if you want your percent overshoot to be less than 20%, you're going to have to go back in and solve. So I did that over here. You're going to have to solve for your value of zeta. Zeta has to be greater than 0.456. You take the inverse cosine of 0.456, and you get this angle of, well, let's see let's just do it this way. So 0.456 inverse cosine of 0.456 multiplied by 180, whoops, over pi, and we got 62.8 degrees, or 62.87. So that value, 62.87. So we draw these angles, and we're here, and everything inside this region meets that criteria. So every point in this region, so this is kind of our limit regions here. So everything here to here to here to here meets our percent overshoot criteria. And that value of K, we can go ahead and solve for. We would just have to pick the point. We can solve for the value of K where that meets that criteria. But we don't have a lot of margin here, right? To keep that down, we see that K has to be less than 0.41. Otherwise, we get too much overshoot. So it's not like we can just increase K forever and ever and ever. We're going to set ourselves up for some potential problems. Okay. This is a built-in MATLAB function that you can use. If you have your control systems toolbox, you can actually use MATLAB to calculate your root locus for you. So if you want to check your work, you can go ahead and do it. But you know what we drew in this presentation up over here, that's the rough version, right? That's doing it by hand. MATLAB, how does MATLAB do it? It just plots 50,000 points or whatever it is. So it does brute force, will do that calculation for you. All right. So the nice thing about this too is in MATLAB, once you have your root locus plotted, you can actually pick a point on the curve and it'll tell you what K is, what this pole is, minus 1.54 plus J 3.02. It tells you damping, or another way to say zeta. Look what else it tells you. It tells me my percent overshoot. And then this is omega sub n, what the undamped frequency would be. All right. Tells you all that information there. One kin caboodle. What if we have a system that is not standard? So what we had before is we had K over here, and then we had a block and a block over here. Okay, so this is H, not K. What if K was not over here? What if it was embedded somehow in the G? We can't use root locus. So this K here can't be out there, right? It has to multiply K times GH. So all we need to do is monkey with the system a little bit. Here's my characteristic equation. Now I'm going to reconfigure it so I have this here, and I take my K and separate it over there. And now I'm going to just rearrange it so that I have 1 plus K times something. The something here is G times H. So this is my transfer function, right? This is my closed loop transfer function. this is how I get my open loop transfer function. I had to modify the transfer function a little bit so that I could get the standard form where K is multiplying it out completely. All right. So I had to tweak it a little bit to get a different open loop transfer function. But ultimately, the characteristic equation is the same. So here's a system. Here's our characteristic equation. We can see that we don't want K over there. We're going to adjust it. Can't get that out of the way. Sorry about that. And then we can move our K over here or K over here. They have the same closed loop poles. They do have different closed loop zeros, but not a problem for us. Okay. Questions on root locus? Because that's the last topic before exam 3, which is next Wednesday. All right, during lab from 2 to 5. Covers everything we've done this semester, but we'll focus mainly on root locus. And was steady state errors on the last test? I don't think so, right? I think test 2 did not have steady state error. So it'll be steady state error and root locus. So that means on Tuesday, we'll do our exam review. And on Wednesday, we'll have the test. I'll put up one of those exam review things for the Tuesday class. You can answer whatever, ask whatever questions, and then we'll do the exam. Exam is just like always, right? You have a note card available to you, but it'll focus more. Again, we've been using stuff the whole semester, like this design parameter, looked at percent overshoot calculations, which is a second order system, but we used it, we applied it for root locus. So steady state errors and root locus. Yes, sir.
I just had a quick question about root locus. So when 2 poles are going to a greater midpoint, how would you tell which one's going to go up and which one's going to go down?
You can't tell.
Can't tell.
You can't tell, it doesn't matter, right? You just know because of complex conjugates, you're going to end up, if you pick a K value that is out in no man's land, it doesn't matter if it's this one or this one, they're both going in whatever direction. So it doesn't really affect the results. So yeah, it doesn't matter. Yep. Standard note card. Just what we've been doing the whole time. What's that? Yeah. And I guess the only thing is, I would probably, for root locus, I would probably, whoops. I would probably, and again, this is totally up to you, but this slide right here has all the rules. Do you need to write them all down? I don't know if you need to write number 1, because that's just complex conjugates. That's what we've been doing even from last semester. Rule number 2, that's a mantra. So start at a pole, end at a 0. Hopefully you have that memorized. And then the next 4, I probably would write down those, including the auxiliary equation, right? To be able to draw a root locus with some level of accuracy. Yes, sir.
What type of systems are really
Mostly what?
closed loop systems?
Well, all the stuff we've done always has feedback, but like steady state errors and root locus, we always looked at the open loop gain of the system. So you'll be given a GH and you most likely will just use the GH. But to get the closed loop transfer function, it's just G over 1 plus GH, right? It's not too bad. So feeling good about it or queasy? I'm feeling nervous because it's been some of the stuff we talked about today. My hope was that this is the 4th time we discussed, a 3rd time. I was a little nervous that people were not answering some of these questions because we did a lot of work, right? And just going back and doing complex math. And so the hope is that, oh yeah, this is just complex math that we've been doing since we did AC circuits. right? Our friends from Eastern Maine, did you all cover how to do complex math that way? Magnitudes, divide magnitudes, or multiply and add or subtract angles? Did a lot of that, okay. That's a lot of what this root locus is. It's just based on doing complex numbers. So it looks scary at first, but then over time you realize, or hopefully you realize it's not that scary. Okay. I do have an example, I think. Where is it here?
You're gonna do a read back.
That's what we said, Tuesday, yep. So I have this example. I can put this up if people want to do it, but it's all spelled out and written out, you know, with a lot of terminology. So I can put that in here. Shows you how to calculate the asymptotes. Shows you how to calculate the, you know, where the asymptotes, the centroid. Then it shows you how to calculate the value of K, where our breakaway points occur. So we end up with here and here. And then I talk about where there no root loci exists. And so I roughly sketched it by hand. I actually didn't even use MATLAB. And then I did the auxiliary equation, right? And then I did, and this is how you do it in MATLAB with root locus. And I checked it that way. So then I just ran through one point, check and see if this is a valid point. My angle is 0. Then I checked it for 5. Then I even showed you how to solve for a value of K. So at 5, you can see I just picked a pole. I got as close as I could. Minus 4.99, I would say that's pretty close to 5. And you can see my gain is 14.7. So that was, again, just a zoom in thing. I couldn't get it perfect. So I can put that up there if you want to see, you know, kind of a fully worked out one with a lot of additional discussion and stuff like that. Or I don't have to, it's up to you. If you think this is too much information, I don't need to. Okay. I will put this up then. All right, that's all I had for today. Any questions? Because we finished with locus, right? Going once. Not sure if you have a question. A lot of smiles. I don't know what I should do. Should I just call class or people not prepared? Is that what's going on? There's a homework, right? And then there's this example here, which I would start off with an easy one. I would start off with one that everything lives on the real axis and kind of do the approach. And then start adding them that have zeros that are not. So like you have infinite zeros and you start getting away from the real axis. And then this last one is, all right, well, I've got to, because like this one is not too bad because I don't calculate angles of departure and angles of arrival, but it does 90% of it. I'm just not stopping at a pole. I wanted to calculate the asymptotes. So if I didn't have asymptotes, that means I have the same number of polar zeros, like the example we just did in class, and I wouldn't be calculating that. And so I think these are pretty good because there's a little more work to calculate these, but I can certainly put that up there. Anything else? I think you all need to think about it, right? Get the weekend. Okay. All right. Have a great day, everyone. I will see you all. So we are leaving a little bit. Take care, everyone.